questions. So it will be short and quick. So let me share my screen with you all. And don't forget to record today's attendance through Spectrum. Okay. Okay. So for tutorial 2, I think the question mainly focus on lecture 6 and lecture 7. So first question is on residual entropy. So what is residual entropy? So by definition, okay, residual entropy can be calculated from spectroscopic data and also measured experimentally. So if the experimental entropy is less than the calculated value, if there's discrepancy between these two values, okay, it is called residual entropy. So that's what you mean by residual entropy, if there's difference between calculation and experimental entropy value. So next part, calculate the residual entropy at 0 Kelvin for a molecule with 3, 5 and 6 orientation having the same energy. So I think this is how the general equation for calculating residual entropy. It is equal to R multiplied with ln S, where R is the gas constant in the unit of joule per Kelvin per mole. So whenever we talk about physical properties relating to energy, the gas constant value should be the 8.314 joule per Kelvin per mole. And S, the ln S is actually referring to the number of orientation, which is given usually in the question. So straightforward, for 3 orientation, the residual entropy would be 9.13 joule per Kelvin per mole. 5 and 6 orientation would be 13.4 and 14.9 joule per Kelvin per mole respectively. So from the unit, it tells you that this is actually in an example of molar properties, because we can see the unit is per mole. So without telling you or writing the molar symbol, okay, you should know that this is molar properties. Okay. So the last question for this question 1, discuss also the suggestion which refute the existence of residual entropy. Okay, so actually there are also some arguments said that there's no such thing as residual entropy. So the discrepancy is actually due to calorimetric measurement fails to detect part of the phase transition to the extent of neglecting value as big as delta H over T. Delta H over T is entropy, okay, for a particular phase transition. So, and at the same time, bear in mind that this order still exists even though at absolute zero temperature, where entropy for solid at 0 K is more than 0. So some scientists believe that residual entropy does not exist due to these arguments, okay, from the experimental part, and also for the fact that actually even at 0 Kelvin, the entropy value still can be more than 0 joule per Kelvin. But nevertheless, this concept is one of the still I think some of the fundamental topics that still being trying to be established or described by fundamental scientists. So question number 2, identify the systems for which it is essential or important to include a factor of 1 over n factorial term on relating or going from canonical partition function to molecular partition function. So canonical partition function denoted by the capital Q, and molecular partition function denoted by the small q. So when we should include a factor of 1 over n factorial when relating these two partition function. So For a sample of helium gas, so it's a gas, okay, so this system is indistinguishable and non-localized. So yes, you have to include 1 over n factorial when you relate canonical to molecular partition function. So for 2b, carbon monoxide gas, so a gas, we cannot distinguish, right, the identity, okay, and also non-localized. So yes, you have to include 1 over n factorial term. And to see a solid sample of carbon monoxide, so it's a solid form of carbon monoxide. So solid phase, solid molecule means that you should be able to locate or describe the position of the molecule because it's very ordered. So in this case, no, you don't have to include a factor of 1 over n factorial. How about water vapor? It's vapor, which is equivalent to, it's another name for gas phase. So for water vapor, you have to include the 1 over n factorial term, okay, when relating canonical with molecular partition function. So third question. Use the equipartition theorem to estimate the constant volume molar heat capacity, so heat capacity at constant volume, for ozone, ethane and carbon dioxide in the gas phase at 25 degrees Celsius. So these are all the hints for you to decide, okay, the equipartition theorem to estimate the constant volume molar heat capacity. So for gas, okay, which we assume it behave ideally, the total heat capacity is given by the following equation. So you can refer to your lecture note. CV, which represent heat capacity at constant volume, will be equal to 1 over 2 nr multiplied with 3. 3 comes from the translational mode of motion, okay, the XYZ description, okay, of the position of solid, usually at 25 most, not solid, usually at 25 most molecule will have translational mode of motion, okay. And then you have to plus from rotational mode contribution, denoted by nu rod, okay, plus 2 new vibrational. So this is from vibrational mode of motion, but you have to multiply with 2. So note that for rotational mode of motion, it will have the value, okay, this nu will have value equal to 2 if the molecule is linear shape, okay. But for rotational mode of motion, if the molecule is non-linear shape, it's band, okay, or tetrahedral, okay, the value of nu rod should be equal to 3. So there are 2 possibility of nu rod value, depends on the shape of the molecule. And for the vibrational nu, okay, you only fill in this part if the total mode of active vibration is available. So it depends on temperature. For vibrational, it should exceed its characteristic temperature, which in this question is at room temperature. Usually most molecules at room temperature doesn't have the vibrational mode of motion. It usually have higher, only at higher temperature, the vibrational mode of motion will be in place, okay. So that's why I say it's important for you to refer to the question. Or in terms of molar volume, okay, we divide everything with number of mole. So that's why it also can appear like this, 1 over 2r, okay, multiply with 3 plus nu rod plus 2 new vibrational. So again, nu rod and new vibrational will have the same justification as the non-molar constant, the non-molar volume, the non-molar volume. So we go back to the main question. Characteristic vibration temperature are usually several thousand of Kelvin. Hence, in this case, at room temperature, temperature is considered lower temperature and has not exceed their vibrational or characteristic temperature. Therefore, the heat capacity at constant volume for ozone. So ozone, if you draw, okay, it is triangular shape. Okay, so it's non-linear molecule. So for the rotational contribution, it should have the value equal to 3 and 0 for vibrational. So this is the value of the heat capacity, 24.9 joule per Kelvin per mole. So again, from the unit, tells you that this is molar properties. As for ethane, okay, again, if you draw ethane structure, it's also non-linear. So it should have the same heat capacity as ozone, which is 24.9 joule per Kelvin per mole. For carbon dioxide, if you draw the structure, it's linear shape. So the value of rotational contribution will be equal to 2 instead of 3. So the heat capacity would be, at constant volume, would be 20.8 joule per Kelvin per mole. So if you notice, question 2 and 3 usually requires, though you know the question, the equation, it requires for you to analyze the condition of the system for you to decide which value to fill in the equation. Okay. So last question on population inversion. So how to obtain population inversion? Okay. So population inversion, usually we're talking about two energy level system. Okay. So for these two energy level system, okay, it can we can make it to be inverse in population by injecting additional energy to a system with to become three energy level system. Because conventional population, you will always know that the lower level would be more populated than the higher one, right? That's the conventional understanding of population. But actually, you can inverse this conventional population, okay, by adding the third energy level. So when you have the third energy level, okay, the additional energy will result in the excitation of molecules to the third energy level. So you can refer to the diagram in the lecture note. But this excitation is only temporary, because eventually this molecule will go down to the second energy level during a radiationless transition, and the population of the second energy hence will become higher than the first level, right? So only at this condition you can see that the second energy level has higher population than the lower energy level, and this system is not in equilibrium. The molecules at second level will also eventually go down to the first level with radiation of H nu light. So if you this injecting additional energy actually usually occur at negative temperature to achieve this population inversion. So do not be so surprised if you see some question and when the question asks you obtain negative value temperature. It is possible, and it tells you that this is how we achieve one of the way to achieve the population inversion condition. So I think that's all for today. Do you have any other question? Tak ada soalan? Okay.
No.
Yes.
No.
Oh no. Just want to tell you that I'm not sure whether you have know or not the date and time for your final exam. Okay. It is scheduled on 1st July at 8:30 a.m. Okay. The details of the final exam, of course, we will post through WhatsApp group. Okay. So I just tell you earlier that it is scheduled on 1st July at 8:30 a.m. Okay. So that's all for today. Thank you. And also give me some time to mark your test and return back to you. Okay, that's all. Thank you.